So, this long question is about too small for me to read on the actual recording video. So, you and a friend are driving. He's going at 65, you're going at 95, and eventually he catches up to you, and it gets to the point of passing you. So, how fast do your speeds compare the moment that those cars are right next to each other in that exact same position for that moment of time? What do you think? They're equal, perhaps? Other guesses? Everybody in agreement that they're equal? I can see Xavier shaking his head. No? That's absolutely right. This is the reason I have this question is one of the big misconceptions is a lot of times if you have objects in the exact same position, even for a short amount of time, that they also share the same speeds or velocities. In reality, they don't. You might be in the exact same position, but just because of that reason, your friend is still going at 95, you're still going at 65. So having the same position does not equate to having the same velocity or the same speed. So your friend's still going faster than you for the answer to this one. And again, I don't mean to do like trick questions like that. It's just I want to make sure to point out the main areas where students oftentimes come into these sections with misconceptions, and that's one of those areas. So
they're equal, but he's still going faster than you.
Well, the positions are equal, but the speeds or the velocities, which is what the question was asking about, those are different. Your friend is still going at 95. You're still going at 65. So you've got different speeds. Okay, so we finished talking about inertia. And inertia is about forces, and it's about diagrams and equations. And as much as I'm sure you missed those, we'll be done for a little bit with force diagrams and equations. We will come back to those not long after we come back from break. Now we are going to delve into velocity and acceleration. And oftentimes this is where physics classes actually begin their material. So if it seems a little elementary today, that's just fine. That's to be expected, and that's good for a change. The reason that I do those types of forces with inertia before this section is because in order to understand velocity and in order to understand acceleration, you really have to know what's going on with those forces for those changes in velocity and acceleration to happen. So the forces are the precursor to what happens with velocity and acceleration. Even though velocity and acceleration are a little bit easier to understand, I still like to start from the beginning, and that's why we began with inertia. So, a little bit about velocity and acceleration. Have your notes out, loosen up your hands, be ready to take a few today. You can label your notes X versus T. X versus T. So in order to understand what we're going to be doing today and for the next, well, I suppose it's going to be dragged out for a long time, probably the next month and a half, because we've got 2 or 3 weeks or whatever for Christmas, plus semester finals. We want to make sure we know exactly what these letters mean. So X corresponds to distance. So you can call this distance, you can call it position, whatever you feel like. Displacement is another term. There's actually a difference between distance and displacement. We get into that later. Distance and position is usually the terminology that we use in this class. The standard units for distance and position is meters, abbreviated just with the letter M. Something else we have to be familiar with here is a triangle. Anybody know what triangle means when you, like, instead of the word triangle, it stands for something? Anybody know what that means? What's it? Difference, yeah, it means change in. So when we're doing the change in distance or the change in position, we have to be very specific about that. And whenever we say that, it means final position minus original position. So when I write final position, I just use the letter. When I do original position, I use the letter with a little O next to it for original. So x means distance, it means position. The reason I use the letter x is because usually it's a horizontal thing. Later on we get into vertical positions and we call that y for obvious reasons. In terms of other things for terminology, we got to know what t stands for. You can probably guess t stands for time, and I don't think I need to go further on that. Time is measured in seconds. Questions on anything so far? Okay. Most of this chapter is putting the velocity and the acceleration knowledge that we have onto a graph. And so today, as you could guess, because we're labeling these notes x versus t, we're going to be putting that information on an x versus t graph. So it's going to seem kind of strange. Your x, or your position, is on the vertical axis, even though this is like the y-axis. X stands for distance or position, and that is on the vertical axis. Time is on the horizontal. That's in meters. This is in seconds. Again, I use cursive S for seconds. Otherwise, my S's sometimes look like 5s.
Is it supposed to be a cursive S, or?
No. Most people just have regular S's. I'm going to move this over a bit. So, the question might be, the simplest thing that we could put on this graph in terms of an object being either moving or at rest or speeding up would be this object at rest at the 0 point. And we call the 0 point the origin. I'm using this little thing as an origin today. You guys remember these from when you were kids? Aren't these the best? Hey.
Oh, the one that like they explode. Oh.
It's still got some oomph to it. Gosh, I wonder how long I had that. Probably got it for like 20 tickets at Shakey's or something. Oh, you guys don't have Shakey's down here. It's like Chuck E. Cheese. Yeah. So, this is our origin. Let's say our object is at rest at the 0 point, right at the origin. If that's the case, we can put that information on the graph, and it would look something like this. The 0 goes here. And as time goes on, that object remains in that position. So we just say it's stationary at the origin. And again, the origin is where we say that 0 is equal to. So again, you've seen graphs before. As the bottom is just time. As time goes on, it shows how your position changes. So you can see our position doesn't change over this entire interval, and our position is at 0. from beginning to end. And that's our graph right there. Another question might be, what if the object is holding still in front of the origin? How would that look? So we'll draw another graph. And this corner represents 0 position and 0 seconds. So any guesses on what that would look like on our graph?
Straight up.
Going straight up like this?
No. Or, I don't know.
It's all right. So the object is holding still, right? So if it's holding still, that means that our graph is still going to be horizontal, because as time goes on, this position is not going to change. And if it's away from the origin, if it's in front of it, then it's going to be somewhere up here, because this represents a position that's not on the origin anymore. So maybe we'd have something like this.
No, that's what I meant.
Oh, it is, okay.
Yeah.
I wasn't sure if you meant like
Oh, no.
diagonal
no,
up.
That was a joke about, like, that was right.
Okay. You're right on the money then.
No.
Everything okay?
When I said, oh yeah, that's what I meant, that was a joke.
Oh, that was the joke. Okay.
Yeah. Oh, I don't know if you could hear the sarcasm in my voice.
Gotcha. It's tough when I can't see your whole face.
Yeah.
I miss seeing all your faces. Eyes can only tell you so much. So it's stationary at a spot in front of the origin. And these are 2 of the 4 examples that we're going to be doing today. Any questions on these 2? Pretty straightforward? Good. Now we got to see what happens when this object actually moves. Those of you at home who can't see anything, I'm using a little Donatello monster truck, so sorry you can't see what's going on here. The table's too low. So, 2 more graphs. Just draw them the same way. Give you a little bit of time to do that, and then we'll see what happens when this object starts to move. I think I will try and see if I can make this work a little bit for the people at home too. So the first example, those of you who are watching, was the object at rest on the origin. This represents the origin. That was the first graph with the horizontal line at 0. The second one was just the object in front of the origin, and that gave rise to the second graph. So, for these next 2, no surprise, we got to have this object start to move. So the first scenario will be this. The object begins at the origin, and then when time begins, it starts to move at a constant velocity away. So the question is, how is that going to look on the graph? So we just have to realize, number 1, at the very beginning, we are starting at the origin. So that means our graph is going to start down here. We're starting at a position of 0, because we're starting at the origin. Now, as time goes on, that distance or that position from the origin is going to grow because it's moving away. So as time goes on, we have ourselves a graph that kind of goes up like this. So we would call that a constant velocity. And you suppose we call this a constant positive velocity or a constant negative velocity? Positive, because it's going up. It's a nice positive slope there. And you can probably guess where this is going next. Now the origin is right here again. The object now starts away from the origin, and it heads towards it. There we go. Like so. Time begins right now. The object is moving closer and closer to the origin, ultimately reaching it. So, how is that going to look on the graph? First off, are we going to start at the origin? No, of course not, because we don't start at the origin. So we didn't start at the origin physically. We're not going to start there on the graph either. Where will we start? Yeah, exactly. Up a little bit higher over here. So maybe we start up here, and then where is this line going to go?
Down.
Exactly. It's going to go down, because we're getting closer and closer and closer to the origin, ultimately reaching it. This, too, is a constant velocity.
Negative.
You got it. And that's that. A couple things I'd just like you to keep in mind for this. When you have a straight line on a position versus time graph, that tells you a couple different things. Most important of which is that you have a constant velocity. Your velocity or your speed is not changing so long as you have a straight line on this graph. Like here, we have ourselves a constant velocity. It's negative, but it's not changing. On the other two graphs, it was horizontal. So our constant velocity was 0, but it was constant nonetheless. So the other thing I want you to just write down somewhere is the fact that on your position time graph, the velocity can simply be found by taking your change in distance and dividing it by your change in time. You've heard velocity is distance over time, and this is just representing that in terms of these graphs. Velocity, of course, is measured in meters per second. And, once again, we are going to be doing a lot of things with graphs in this section. And if they had no bearing on the real world, I wouldn't waste our time with them. But they do. And this is one of those examples. The slope of a position time graph immediately tells you your velocity. And if you look on your equation sheet, in the bottom section, or your equation shirt, as the case may be, it says right here, x versus t slope equals v, or velocity. So that's the important thing you got to know about these graphs. Of course, if the line isn't straight, if it's wiggly or curvy or changing, then if you go, change in distance over change in time, you'd get an average velocity. But if you do have a straight line, it'll tell you your instantaneous velocity there. Okay. Anybody know the difference between speed and velocity? We kind of use those terms interchangeably. Did you know there was a difference?
No.
Yeah, so when you say speed, it's talking about your entire distance traveled divided by time. So speed would be like your entire total distance that you've covered divided by how long it took you to go that far. Velocity, so I guess I should say this is like speed. If I want to say it that way, then this would be speed. But in terms of velocity, when we're dealing with change in distance over change in time, what we're really talking about is we're talking about displacement. And what displacement is it's the distance from the spot you started to the spot you ended. So if you run the 400 meters, what is your velocity over that period of time? It's going to seem strange, but it's 0. Because for the 400 meters, you go around the track once. You end in the same place you start. So your total displacement, or your total distance between those 2 points is 0. So your overall velocity then would be 0 for that. And so when we're dealing with our position, our x values here, generally what we're talking about is displacement. So on the worksheet, if we need to do something different for speed and velocity, it'll specifically tell you which one you're looking for. But yeah, speed is your total distance traveled divided by time. Displacement corresponds to velocity, and that's your total difference between the spot where you start and where you end divided by time. That's what displacement is. Questions on any of this? Okay. You guys are going to have a good amount of time to work on the homework. This is wonderful.